Good morning, everyone. I'm Dr. Yashata. Today I'm here to speak about dispersive power and resolving power of a grating. So this topic is under diffraction, which is in the AKTU syllabus for engineering physics. So these are the two major parts we're going to discuss. First, we're going to discuss about the dispersive power. So the dispersive power of a grating is generally defined in the terms of the incident wavelength which is used, and it is basically the variation of rate of angle of diffraction with the wavelength of light used. So the formula for our dispersive power can be termed as d theta by d lambda, where lambda is the incident wavelength and this is the incident wavelength, whereas theta is the angle of diffraction. So how the angle of diffraction is varying with the incident wavelength. So that is basically the dispersive power. In order to obtain the expression for dispersive power, we need to take the condition of principal maxima for diffraction for diffraction at n slits. The formula for principal maxima condition at n slits is a plus b sine theta is equal to n lambda, where theta is angle of diffraction, n is the number of order of the principal maxima, and a plus b is termed as the grating element. So from these two elements, A and B, one is the opacity width and other is the slit width. So here, when through this equation, if we differentiate in this equation, we can see A plus B is constant, N is constant. So we're going to we differentiate this equation with the two terms. So we can differentiate equation 1 with respect to theta and lambda. So when we're going to differentiate this equation, so what gonna we obtain is that so a plus b is constant, so it will be written in so manner, and sine theta will be converted into cos theta, d theta, n is constant, and lambda can be written as d lambda. So if we rearrange this equation, d theta by d lambda can be written as n divided by a plus b cos theta. So this is the expression for dispersive power of a grating. So this is the expression for dispersive power of a grating. So here what we can find is that, so dispersive power, so what we're going to find is that dispersive power of a grating is directly proportional to from this formula we can generalize directly proportional to the n, which is the number of order of the principal maximum. And again, this dispersive power is inversely proportional to the grating element. It is inversely proportional to grating element, and it also inversely proportional to the cos theta. So what we're going to infer is that if theta is actually for diffraction, we have a very small angle of if we have a small angle of diffraction, so then cos theta value will be, again its value will be very less. So what's going to happen is that, so in that case, as it is inversely proportional, dispersive power will be very high. So lower be the diffraction angle, higher will be the dispersive. Now, if we can compare this dispersive power in terms of the constraints of white light, so from violet to red, so as theta for red is greater than theta for the violet light, so from the visible spectrum. So from the visible spectrum, if you're going to compare this, so theta of red is greater than theta of violet. So what's going to happen is that, so dispersive power of red region will be high than the dispersive power of the violet region. So the reason for this is that because the dispersive power is not inversely proportional to theta. It is inversely proportional to the cosine of theta, right? So the dispersive power of this red light get more dispersed in comparison to the violet light. And if we say theta is very less, so in that case, theta is approximately 0. So in that case, so if theta is, so going to happen is that, so cos theta will be approximately equal to 1. So in that case, our value of d theta will be proportional to d lambda, we can write, because the other parameters in the equation, so if you're going to find this equation, so this parameter n by a plus b, this is actually constant. So it will be that theta is directly proportional to the this particular thing. Now, this condition is termed as normal spectrum. So under normal spectrum, angular dispersion of two spectral lines in a particular order is directly proportional to the differences in the wavelength. So if the spectral variation is equal to the angular variation, then we term it as normal spectrum, right? So this is generally very rare condition. Sometimes this happens. So this is the thing we're going to add for the dispersive power. Moving over to the resolving power concept. So resolving power is basically the ability of any device to resolve two spectral lines. So how we can resolve an optical instrument, how finely we can resolve an optical instrument. So if there are very two side-by-side spectral lines, can we distinctly view them? So that is defined by resolving. So in order to set the limit of this resolution, when we can say that the two spectral lines are clearly visible, so this limit was given by Rayleigh. So according to Rayleigh's criteria of resolution, so when the, according to this criteria for diffraction, let us assume we are having two spectral lines. One is a wavelength lambda and other very close to it is by difference of d lambda is lambda plus d lambda. So this is the variation diagram of this. Now here it is the maxima point of it. So the other line, I'm going to show it by the dash pattern. This type of pattern you can obtain. So this is the spectrum for d lambda. If you're going to obtain such type of pattern or observation for two spectral lines, then the lines are said to be just resolved. So according to Rayleigh, if the principal maxima of one spectral line, which is this point, falls on the first minima of the other spectral line, then we term the two spectral lines are just resolved by this grating. If we are having a condition beyond it, say for example, we are having the condition this manner. So this is the spectral diagram. This is the principal maximum, secondary maximums. Again, this type of diagram we are having. And for the other wavelength, we are having this type of diagram. So in this case, the peak for lambda and lambda plus d lambda are quite far away. So this case is highly resolved case. But if the two spectral lines are so close, So in this particular case, actually what we're going to observe is that uh, this point, because it is the maximum of these two. So here the point of observation will be of this type. This type of pattern we're going to obtain. And here we're going to find a dip in the intensity. And these are the maximas for lambda, and this is for lambda plus d lambda. So if we're going to observe this type of pattern, two maximas which are uh, slightly separated by a bit of lesser intensity, then this condition is known as just resolved condition. If further the spectral lines are close, then the case will be of not resolved. So this is the case of highly resolved. For not resolved condition, I'm going to have this type of pattern. So in this case, maxima of the one is not falling on the minima of the other. So in this case, this is the maxima of lambda, and this is the maxima of lambda plus d lambda. So what we can observe is that this peak will be this point will be lead to the resultant intensity in this area. And here we cannot find any separation in intensity. So this type of pattern will be observed. So here we won't be able to find any two maximas which are separated by some weaker intensity. We can obtain just one stronger intensity. So this case is assumed as or termed as not resolved according to Rayleigh's criteria. So this is very important topic. So this help us to identify how the two spectral lines are resolved or not resolved for a grating. And this resolving power of grating highly depends upon the number of lines on the grating, capital N. It depends upon capital N. So in the next lecture, we're gonna obtain the relation for resolving power of a grating, and we're gonna see how this value depends upon the total number of lines on the grating. So before that, we even need to know that in this particular part I discussed, this is the point where we found the minimum intensity. So what is the intensity of dip? So this expression is also very important. So in order to obtain the value of this intensity, very small derivation we are going to have is, in order to obtain the value of this intensity at dip. So we're going to take the condition of Fraunhofer diffraction at a single slit. So intensity expression for Fraunhofer diffraction at a single slit is such as, so this is the expression for Fraunhofer diffraction at a single slit. So this type of intensity pattern we can observe for both the lights, for light with wavelength lambda as well as light for wavelength lambda plus d lambda. And the point of dip is actually, so this is the point of maxima at 0, and here it is the minima is at pi. And for the other case, we have this expression. So this point will be somewhere between 0 to pi. It means the dip point is basically at alpha approximately pi by 2. So if we're going to keep this value of pi by 2 in this equation, so sine square pi by 2 by pi by 2 whole square. Now this value is 1. We're going to obtain 4 I naught by pi square. So this is the due to, say for example, intensity lambda. Likewise the same for d lambda also, we're going to find the same intensity. And the resultant intensity at dip will be summation of both these intensities. So this value will turn out to be as 8 I naught by pi square. Right? So we can term this that the resultant intensity at dip, you're going to solve this value. The resultant at dip is found to be 0.81% of the incident intensity I. So sometimes this expression is asked, and it's a very important expression. So I hope so you found this video useful. In this we discuss what's the dispersive power of grating and what is the resolving power of a grating, and at what is the minimum intensity at dip. I hope so you found this video useful. This is the books from which the content for the present videos have been taken. Thank you so much for patiently watching these videos.